Okay, if we looked at the evolution of the machine learning algorithms, we would see that there are a lot of things that are changing very rapidly. So anyway, at the first lecture, we were just like introducing the main concept of machine learning and supervised learning. So we
Mm,
didn't really dig deeper in any of the concepts. It was just like an overview of what we will be doing. So we talked about AI and how everything really started from people trying to think about automating things. So instead
mm,
of doing everything yourself by hand, you would think about automating everything. Okay. So like having a machine or having a car or even a washing machine to help you do a lot of things. So that was like the main idea. So it's all about automation. And
mm,
then people started thinking about like making machines. So the machine would be built upon using conditions. If there is like a threshold, if it exceeds the value of this threshold, then you get to do a specific thing. So everything was really hard coded in this way. But then people started to think about this, how to make this machine smart, how to make this machine able to make decisions. Okay, so
mm,
like the beginning of AI really started in 1940s, so it was really early. And then people started thinking about like developing algorithms and automating the behavior of algorithms, such that we have a lot of if conditions, we have things that can really help us to achieve good results and automate the algorithms. And then we see the machine learning era, the machine learning algorithms, and we see how we can build something like a perceptron or something easy like this and really try to automate the behavior of such machine learning algorithms. And we will be talking about these kind of algorithms later in the course. And then we see of course, the rise of big data and the emergence of deep learning algorithms, and we currently see a lot of very nice deep learning algorithms. For instance, like the transformers and the attention-based algorithms, and really, like machine learning are in every field right now, and we see that they are like having a very huge success in image classification. So in image classification, there is a huge literature and a huge number of publications going into image classification, and of course video as well, and also NLP, natural language processing. So have you heard about ChatGPT?
yes.
So it's a huge deal because it means that really the machine can really think about what we are typing and try to
Mm,
make decisions and really come up with smart solutions as well. So that's a huge part of supervised learning, all of these algorithms. And we also have reinforcement learning, which is not covered in this course. But anyway, the main idea is that we try to make the machine not really supervised, so it doesn't know the identity of everything it has, but it tries to have like a path and really think about what to do in order to maximize a reward. So for instance, if you enter like a website like a chess.com and you looked at the like if you are playing against an AI, this AI
mm,
is built using reinforcement learning. So it really tries to know like the best scenario or the best next move in order to maximize the reward and win the game. Okay.
mm,
Okay, so that's very quickly what we were trying to say in the first lecture. And just to give an idea of how strong supervised learning is, I said a lot of things in the past lecture or the past slide, sorry. But actually, what is really nice about supervised learning and AI, that everything in the last lecture was actually artificially generated. So I didn't write anything in the last
oh,
last slide. So that was like a way for me to show you how awesome this is right now.
mm,
Okay. So all of this is you by using something called the Notion AI. Okay, and you can try this yourself and see how really advanced this is. And this is all behind the scenes. I was just taking this copy and paste. I didn't edit anything. Okay, so okay, so we will be really trying to know how to automate such algorithms and how to perform this kind of supervised learning. Okay, and ChatGPT right now is really advanced. So that's like, for me, that's the best example for showing the strength of AI right now. So we go ahead, please, and see this video with this senior developer giving ChatGPT some questions, which were actually interview questions at Google, and it was able to pass the interview, which is uh, outstanding, of course. So, okay, so in this course, we would start with why. I would really try to adopt this approach by starting with why we are doing something. So instead of just presenting an equation and just telling you that this equation is calculating something, we would try to think from the perspective of the engineer. So let's like discriminate between two things, like a user, okay, and engineer, because an engineer would think about how something is done and how to come up with a new solution. On the other hand, a user will just make use of the technology. A user will just get an equation and will just substitute in the equation with the required numbers. On the other hand, an engineer will really think about the problem and think about why I need to develop an equation and then come up with an equation. So we are engineers. We need to know everything and where it comes from. Okay. So if you have any questions during the lectures, please just interrupt me and ask questions. That's totally fine.
Okay.
So regarding the references, we will be using different references. There is a very nice course on Udemy. It's introducing linear algebra, okay, in very nice details. So go ahead and check this course, and don't worry about it if you cannot purchase this course, because I think it wasn't for free. We will be trying to cover all the concepts of this course, of course, those that are relevant to machine learning. Okay. And we have two books, and we will be using some concepts of them. So we wouldn't be using a lot of like the whole book. We'll be just cover some concepts from them. So that's the first one, Python machine learning, and the other one, pattern recognition and machine learning. And we will be using some of the lectures by Andrew. I don't know if you know him or not, but he's one of the most popular people. He's really famous in machine learning and deep learning community because he co-founded Coursera. Okay, and he has a lot of courses in machine and deep learning as well. And you can actually order the course and just listen for the course for free, which is really nice. So we will be using different references in order to develop our course. Okay.
Mm.
Okay, so I think, uh, and of course, we'll be using like papers. So I would like to see if there are like new papers that are coming up every day so that we keep up to date, basically. Um, so in that first lecture, I also talked about the difference between supervised and unsupervised learning. So the main difference is that in unsupervised learning, we don't know the nature of data. With supervised learning, we know the true identity of our data, and we call this labeled data. Okay, so let's just imagine that we have multiple dogs, okay, and multiple cats, and we need to develop a machine learning algorithm. We need a machine to make a decision and just differentiate between uh, dogs and cats. Okay, so we decided to take two things, two measures, and we call them, in machine learning, we call them features. Okay, so we take one feature from the dog, and we take another one from the dog, and the same two features from a cat. So let's say that the first feature was like let's say the weight, okay? And the second feature was the height, okay? So we have this, one from a dog, one from a cat, okay? And let's say that, of course, the weight of a dog will be like higher than the weight of the cat, okay? So the thing is, we need multiple instances of that dog to be able to differentiate between a dog and a cat. Okay, so what we do is we collect a lot of samples. We name this samples. Okay, so let's say that we collected, let's say 100 samples, okay, for a dog, and we collected two features as we said, so the weight and the height. Okay, and then we collect another 100 samples for the other class, which is cat. Okay, and those are belonging to.
Sorry, I want to ask what exactly are the samples? Is it like the object itself or the features?
Yeah, yeah, the object itself. So that's from one dog. So the first sample is corresponding to one dog. Okay,
Okay.
and the second one from another dog. Okay,
Okay.
so you're basically trying to create like a distribution or like a lot of variations. So you're taking a lot of samples from the same animal, basically.
Okay.
Okay, so now that we have collected these 100 samples from dog and 100 samples from cat, we tend to think how to differentiate these two. Okay, so right now let's use some terminologies. Okay, so what we collected here is the feature. Okay, so those are features and
Hmm.
those are samples that we are collecting. Okay,
Hmm.
and the true identity, which is something very important in machine learning, is called true label. Okay, so the
Hmm.
true identity of that animal is the true label. And because we are dealing with machines, we really need to digitize everything. So you cannot put dog or cat. So we just encode this with a number. So let's say that this will be 1 and the other one will be 0. Okay,
Okay.
such that dog is corresponding to the value 1. Okay, and this is a true label, as we said, and the category is called a class. Okay,
The
S-
category of what?
so of animal. So we have dogs and we
Okay.
have cats. Okay,
Yeah.
and this is also called a class. So in this problem, we have two classes. Okay, and we also in machine learning we call this a binary classification. Okay, because we only have two classes and we can encode them by saying that this is 1 and this is 0.
Sorry, I want to ask, can you like put them in one class and
So the main reason we're doing this because we would like to differentiate them. We would like to see the difference between them. Okay. Actually, and on the other hand, as you were saying, when we put them in one class, that's precisely unsupervised learning. Because with unsupervised learning, it's like you are entering a dark room, okay, and you know that there is an animal inside. And then you are just picking up the measures from that animal. Okay, so you are just picking up the weight and the height
okay, you
from
don't
many,
know?
many, many samples. Exactly. You don't know the true identity of that animal. Okay,
Okay.
that's the big difference. Okay, so you are picking up the measures, picking up the features, but you don't know the true label. This is unknown. So the true label is not something that you know. Okay, so this is a different problem from supervised learning. So in unsupervised learning, we try to do something like clustering. Okay, we try to do something that really gathers like those samples. Okay, and say, okay, these samples are behaving similar to each other. So most likely they are belonging to one class. okay, to a class, but I don't know if this is a dog or this is an elephant or anything.
Mm.
I really don't know the label, okay?
Yeah.
I'm just trying to infer this information from the data, okay? Because they are similar to each other. These values are like clustered next to each other, okay? And I'm trying to do also the same for another cluster and say that they are behaving together or they are behaving similarly, then they are most likely belonging to a different class, okay? So in a sense, unsupervised learning could help me put the true labels to a supervised learning problem. Okay.
Mm.
If I don't know the true identity of my samples, clustering and supervised learning in general could in some way help me to label my data. Okay.
Yeah.
Okay. Do you have any questions so far?
No.
Okay. So this is, of course, like a very general idea. We didn't like talk about any algorithms or anything. This is just
Mm.
an overview. Okay. So in supervised learning, I would say, as we said in the last slide, we have many samples and we collected
Features.
two features like so. In unsupervised learning, we are still collecting features, but we don't know the identity. Okay. So let's talk briefly about something which would be actually relevant to the talk of machine learning. So imagine that we have numbers. So when people in the beginning talked about numbers and they came up with the number line and they thought about numbers, they were thinking that, okay, we should be counting everything that we see in a physical sense, okay? So you cannot really talk about something like zero because it doesn't make sense. It doesn't really exist, right? You cannot
Yeah.
count zero in reality. So it was always like this. People were just thinking about numbers from 1 to, let's say, 10 or 20, anything that they can count. And then, like philosophers and people like that, then they started thinking, okay, but there is an issue. What will happen if I give you an apple and then I took this apple from you? Then you don't have any apples, right? So you
Mm.
should be having zero apples. There should be a number that would express that I give you zero, I give you one, and then I took one from you, okay? I
Mm.
should be able to express this kind of mathematical equations. And then they came up with this zero number, okay? And then they
Yeah.
said, okay, let's fit this on the same number line because it's expressing a value as well, okay? And then they started thinking,
Yeah.
okay, what will happen if we would like to solve this problem 1 minus 2? Okay, so this is a very relevant issue. And then they started to think about, okay, we need to include something that is like mirroring the effect of one, which is minus one. Okay. And then they came up with the negative numbers and they said, okay, if this is mirroring this effect, let's put them on the other side. So let's come up with these nice negative numbers to be able to solve a mathematical issue. Okay. So if you try to really recognize a pattern in what we are trying to say in this, that people are trying to always solve a mathematical issue, right? You have a problem, you have a mathematical issue that you are trying to solve using those numbers. And that's how we are extending our vision, we're extending our knowledge by doing so to solve a mathematical problem, okay? So let's discuss something which is also relevant and will come in handy when we talk about deep learning algorithms. So something like a complex number. Okay, so even if we don't cover this in this course, it would be nice to know where this is really coming from. So something like a complex number is quite challenging or quite actually different from those numbers because people started to think, okay, we can't take the square root of 4, right? You could say that this is 2. So what will happen if we are trying to square 2? we get 4. And that's really the very definition of taking the square root such that you can go to 2 again. Okay, so is there any number for which we can take the power of 2, so we can square this number in order to get something negative? And then they came up with the number I, okay, the imaginary number, okay, such that it will solve this issue for me, because then when I take the square root of -1, it will be I. Okay, so they came up with a solution to this. So right now, again, it's the same concept. You have a mathematical issue that you need to solve by introducing a new number, and then they came up with this complex number. Okay, and there is now a different issue: where to put this number, where to put this complex number. It's not very straightforward where to put this number, right? Because with the other numbers, we were just using the same line, right? But with
Yeah.
this, it's a little bit different, because let's just imagine that you want to put one I, okay, which is the first imaginary number. The imaginary number is different from the other numbers. So you cannot, like, after 5 or after, let's say, 100, then it will become imaginary, right? Because
Mm.
the imaginary number is representing something different. It's a different entity, okay? So that's why they came up with a different axis, a different axis. If this is our x-axis, if this is our real number axis, then we have to come up with another axis, the y-axis, okay, to represent the imaginary axis, okay? And then they came up with this. And by the way, in geometry, we represent anything that is uncorrelated with this 90 degrees angle, okay? So this would mean that the x-axis is uncorrelated with the y-axis, okay? There is no correlation between them, meaning that the change on the x-axis does not really influence anything on the y-axis, okay? It doesn't cause any change on the y-axis, okay? So here you have a number like 1i, 2i, 3i, and so on. And here you have -1i, -2i, and so on. Okay. Okay, so do you have any questions so far?
No.
Okay, cool. So now let's try to represent one of our complex numbers. Let's say we are landing on this point, okay, which is 2 and 2i, okay? This number right now is not just a number, because it has two physical entities. It has the real part and the imaginary part. So it is really like extending and going beyond the normal definition of numbers, because it has two numbers. So it's really a vector, okay? It's really a vector. It has a real part, 2, so the projection on the x-axis, and it has a projection on the y-axis, which is 2i. So if I'm gonna put this as a number, I will just sum these two together, okay? I would say that this is 2 plus 2i, okay? So that when we look at this number, we'll just know that this is the real part and this is the imaginary part, okay? So right now, when we look at this number, when we look at this complex number, we would just know that this is not really just a number. This is an actual vector. This is a vector in this 2D space, okay? So right now you have a number, something that we call a number, that could be nested in a 1D space. Let's say a number 2 or a number 3. It's only a real number, right? So this is nested in a 1D space, okay? Because it never goes in this second dimension, right? So it's nested in 1D, okay? And if we have something complex, if we have something represented in two dimensions like that, it's still a point, right? It's still a point, but this point is nested in a 2D space, right?
Mm.
Okay, that's exactly, this is parallel. This concept is parallel to what? This concept is parallel to what we are doing here with the features. Okay,
Mm,
because here we have height and we have width. If we are going to scatter these points in 2D space, then we would, let's say, use the value of this feature, which is the height, for the x-axis, and then we would use the value for the second feature, which is the weight. We will plot in this one on the y-axis like so. Okay, and then we would have one sample, right? So let's
yeah.
name this sample, let's name it x1. Okay, and then to represent x1, you would represent x1, it's a point, but this point is nested in 2D space because you have two features. So you
Mm,
can put x1 here, which would correspond to a specific height and a specific width, okay, according, of course, to these two values, okay? So if we
mm,
have a value 2 here and 3 here, this will be 2 and this will be 3, okay? Okay, so it's like 2 with all the other samples. So let's say that this is x2 and this is x3. We'll just go ahead and scatter all of these points in this 2D space, okay?
mm,
And it would be useful to think about what would happen if we extend this space, if we have more features, okay? You would just think about this again as a point, but the point is nested in a different space. So if we have another feature, then we would have another dimension. And x1 would still be a point in this high dimensional space, okay? But it would have a projection on x and y and z, okay? Any questions?
mm, no.
Okay. Um, okay, so right now with a complex number, I was just like explaining this to make the idea of complex numbers easier to understand. We can like in any way describe this complex number. Just for your information, we can describe this with two things. We can describe this with the magnitude, which is the length of the vector, and we can describe it with phase, which is the angle that this vector is making with the x-axis. Okay.
Okay.
Okay. So going again to unsupervised, we would say that with these samples in the supervised, we know the identity of them. So if we're going to scatter some of them belonging to dog in red color, we can scatter some other samples and represent them with white. Okay, like so. And the main concept or the main core idea of supervised learning is that we need to draw like a boundary that would separate these points from the other points. Okay,
Mm,
so we need to come up with a line in the case of linear classifiers. We need to come up with an equation with an equation for a line that would separate these two data sets. Okay, so we
yeah.
need to separate this one from this one. Okay, so that's how the classifier is making decisions basically, because we know if we are going to substitute a value in the equation of that line, any number that lies on this, any any sample that lies on this line, the equation for it will be zero. Okay, and anything higher than this line, the equation, when we substitute in the equation, it will be positive, and anything below that will be negative. Okay, and that's
Mm,
how we are making decisions. Okay, we need just an automated way to come up with the line, and then from the sign of the sample, we would know the correct class or the correct category of this animal. Okay.
mm,
Okay, the idea is different for unsupervised learning, because for unsupervised learning, we would have the points without knowing the categories, and we would just scatter all points like that. We'll just scatter all of them. Okay, with unsupervised learning, we need to come up with an automated algorithm that will just try to say that this is cluster one, that this is our first cluster, okay, and we have, let's say, perhaps another cluster in a different region. Okay, we have another cluster, let's say here, cluster 2. Okay, so the
Yeah.
objective of supervised is to discriminate between classes, and supervised to try to cluster those perhaps the classes that we have. Okay,
Yeah.
okay, so I think that was almost everything that we covered in the first lecture, and feel free to look at these points, because these are like the main things that we're gonna cover in the course. Okay, we will cover some linear models, some nonlinear models, okay, and we really would hope to look at neural networks and deep neural networks as well. Okay.
Okay.
Okay, so do you have any questions in the first lecture?
Yeah. So the main difference between the supervised and the unsupervised is the linear classifier helps us to know the true label in supervised, while for the unsupervised is clustering that happens.
Yes, yes. For supervised, you have two classes, you have two categories, and you need to discriminate them in an automated way. In unsupervised, you
Yeah.
don't know the true identity, and you just need to cluster them or just measure their similarities and just say that they are behaving together, then most likely they are belonging to the same animal. Okay?
But you can't like get them as a true label.
Yes, yes. You can actually use, as I said in the beginning, you can use unsupervised learning to try to help you to label
Yeah.
your data somehow.
Yeah.
And this would say, okay, that this is animal one and this is animal two.
Mm.
But you would never be able to tell what what will be the true identity of that animal. You just say that these data, these like scattered points are behaving similar to one another. Okay. Okay, so by the way, even in lecture two, I was just trying to introduce some things in linear algebra. So we still didn't go deep in um, like the supervised learning part. But the thing is,
Mm.
it would be helpful, of course, to like
Understand.
revise some things from linear algebra, because it's really, really relevant to what we are doing. Okay.
Yeah.
So let me just open the lecture. Okay, so in linear algebra, we are basically concerned with vectors, okay? And of course, we need to mention matrices, and we need to mention scalars, because each one of them is doing something interesting in linear algebra. So in machine learning in general, we will be all the time using a matrix, using a vector. So we need to think about them in a visualized way to try to really know what they are doing, because that would make everything easier later on. Okay. So a scalar is actually coming from the name. What like the function of a scalar is coming from the name. So a scalar is doing scaling. Okay, it is scaling my elements with a specific number. So for instance, if we have the number 2, which is a scalar, okay, if I multiply this with a vector 1 1, this is going to give us 2 2, right? So this
Yeah.
scalar is going to each element of the vector and just scaling this element with its value, right? So that's
Yeah.
why it's a scalar. So to take a nice approach and really try to see what is happening, if we have a vector, our vector, which is 1, 1, this would mean that this vector has two values. It has one on x-axis and it has one on the y-axis, right? And then we can represent this vector like so. We can have this vector like so. Okay, so now what is happening with the scalar when we multiply this with the scalar, we are just going from 1, 1 to 2, 2,
Okay.
like so. Okay, then why are we visualizing this? Why is it relevant to visualize this and really think about this in a visualized way? Okay, so it's important to think about this in a visualized way because if we look at this and what this scalar is doing, imagine that this number is 4, okay? Or this number is actually minus 2 or minus 4 or negative 100, okay? Can you recognize a pattern? What is happening?
Goes in the same direction.
Exactly. So the direction is the same, okay? What does this mean, okay? Like a physical thing. We say that all of these variations of the same vector are the span of the vector, okay? And the space in which this vector is living, this vector is like a living vector. It's living in a subspace, okay? So we could say that this is the subspace of the vector, okay? Everything that the vector could see, okay? And all of these variations are the span of the vector, okay? And what the scalar is doing, it's not changing the direction. So the direction is always fixed, okay? But it's just changing the magnitude, okay, of the vector. So it's just changing the scaling of the vector, okay?
Sorry, I don't understand this subspace.
Okay, so the subspace when you are not changing your direction, okay?
Okay.
And because the scalar is not changing the direction, so we are still talking about the same subspace, okay? If I'm saying that this is another vector, then I would say that the subspace of this vector is different from our original vector because now the direction is different, okay?
Okay.
Okay. Okay, let's go to another one, which is vector, okay? And as we said before, a vector is just a number, just a sample basically, and this sample is nested in a high dimensional space, okay? So we could say that this is just a sample. This is just a sample, okay? And this sample is actually a sample nested in, let's say, MD space, okay? Multi-dimensional space, okay? And as we said, if we have one number, then we're just talking about x-axis. If we have two numbers, then we have a point nested in a 2D space, three numbers, 3D space, and so on. Okay. So what would happen if we are taking a vector and then we are multiplying this vector with another vector? So let's say that we took this vector and we are multiplying this vector with itself. Okay. Something like that. As we know, we will take the first element, multiply it by the first element, because this is a dot product now, okay? This is a dot product. So we take all of this and just multiply it by this. So the first with the first element, and the second with the second, and the third with the third, okay? And the fourth with the fourth. We multiply them and then we add them together, right? So this would give us one value, right? So eventually a scalar, okay? So what is happening here? So what is like the physical meaning of that scalar? What does this scalar really represent? Do you have any idea? Okay,
No,
so
no. So I forgot I muted. No.
okay, so When we multiply this vector with another vector of equal length, of course, like so, what we have here from the dot product, we can say that this is also a measure of similarity. Okay, it's a measure of similarity, of course, when we like normalize for the scaling after that. But this is another thing that we could extend um, on in a different lecture. Okay, but we could just say that this is a measure, a very simple measure of similarity, because if all the elements are looking the same, okay, despite the scaling for now, if they look the same, then the value of that scalar will be high. Okay, if they are
Okay.
different,
Okay.
they will be this value will be small. Okay.
Uh,
All right. So what about matrix? What is the matrix is doing? Why are we talking about scalars and vectors while actually in machine learning, majority of things are in matrix? Because the matrix is doing scaling and it's also doing something different, which is rotation. Okay, so with a matrix, what you are doing, you are transforming your vector, you are transforming your data, but you are doing two things together. You are scaling your data and you are rotating your data. Okay, so let's say if you have a vector like this, if I'm applying a transformation matrix, this matrix could knock off this vector from its original direction and scale it as well. Okay, so it can do scaling and rotation at the same time. Okay, is this clear?
so what makes it change direction?
It would change the direction because a matrix will, let's say, look like this. Let's say that we have a matrix like that, and we are multiplying this with our vector. Okay, so let's say that this our vector. This is our vector. Okay, so what is happening now that you are taking this value, multiplying with this value and this one with this one, okay? But all of this to get the first element, right?
Mm.
So right now you are changing the whole vector. You're not just changing the scaling of the vector. Like you are just, no, you are
Mm.
trying to come up with a new vector, okay? And when you take this one, multiply with this one and this one with this one, you are gonna come up with a new value, okay, which doesn't necessarily relate to this one and direction, I mean, okay. So
Yeah.
with it change the direction and it could also change the scaling, okay. And
Mm.
by the way, I'm just giving a very summarized example here, but there is some transformations like translation,
Mm.
okay, and rotation, okay, that are very, very popular in graphics. Okay, so you have something like cosine, cosine, and sine, sine, where you transform your data and apply some rotation. Okay, but that's something else, and I'm not really like perhaps I'm not memorizing this correctly. But the thing is, there is some kind of transformation that is going on. Okay, and as we can see from this very like small example like here, that this is not just as changing the scaling, this could also change the direction because it's giving you a whole new vector, a completely different vector. Okay.
Yeah.
Okay, so let's try to think about something else, which is adding two vectors. What would happen if you add something like this, like 1, 1, okay, plus 2, 3, okay. Visually, what is happening here, of course, the result would be that you are summing you are adding these two together, so it will be 3, 4, right?
Mm.
So what would happen here if we looked at 1, 2, 3, and we look at this, is that you are taking the vector that was here, 1, 1, okay, and you are adding this to another vector, 2, 3, which is here, like that. Okay. So the result would be as if you are taking, as if you are taking one of these vectors. So let's say that we're taking the long one, okay? And you are just sticking that vector on top of the old vector, okay? Head to tail, like so, okay? So I'm just taking this vector. I'm just sticking this vector here, okay?
Yeah.
When you are sticking them like so, you will end up getting the value 3, 4. Okay, so that's like the geometrical approach of thinking about addition, like so, sticking the vectors head to tail like that. Okay.
Yeah.
Okay, so let's go to another thing which is also relevant to what we're trying to say in machine learning, which is what is the determinant of the matrix? What is the determinant of the matrix? Okay, we can think visually about the determinant of the matrix as well. If we imagine that we have an area like that, this area is governed by, let's say, three vectors. So this one, and let's say this one, and this vector as well. Then the determinant of the matrix is what would be the transformation that will happen to this area. So let's say that we took this matrix, okay? We multiply it by a vector, okay? What will happen to this vector, or what will happen to this area that we are talking about here, okay, is the determinant of the matrix. So let's say if we apply our matrix, which is, as we said, a transformation, it gave us this area, okay?
Mm.
So if this area was A, the original area, and the new area is 2A after transforming with the matrix, this would mean that our determinant equals 2, okay?
Mm.
So our determinant visually is the change of the area, okay? Is the change of the area. Of course, this area is not fixed. Does it have to stay in the same direction like so? It could be like a square in the beginning, but after doing the transformation, all of the sudden it turns like that. The thing is, if this is A, and this is 1.5A, we could still say that the determinant equals 1.5, okay?
Mm.
So it's the change of the area, okay? Okay, so we could also perhaps talk about something which is the neutral number in multiplication. We know that when we are multiplying 3 and 1, we'll end up with 3, okay? So we know that the neutral number in multiplication with numbers is 1, right?
Yeah.
But what is the neutral matrix? Okay, neutral would mean that you are multiplying something with it and you end up with the same thing. Okay, so you are not moving, you are not doing anything. Okay, in our talk about matrix, what is neutral is the identity matrix. Identity matrix. Okay, and it's represented by ones on the diagonal, like so. Okay, so what makes this matrix really special is that if you take, it's really like one, but for a matrix, okay? So this identity matrix, let's say that we have our matrix A and we multiply this by our identity matrix like so. So what would happen is that you take this multiplied by that, which will give you A, right? You take this multiplied by that, will give you 0, right? So this would be A plus 0, right? And then
Mm.
you take this multiplied by that, will give you 0, right?
Yeah.
Or we could take, or we didn't take this with the second column. So let's take this with the second column to just put the second column as well. So we take this multiplied by 0. So this would give 0. Take this multiplied by B, which would give B. Now we take this multiplied by this, C, and this will give 0. And this with this will give D, right?
Yeah.
So the thing is, you ended up with the same matrix, right? With the same matrix, A, B, C, D, right?
Yeah.
So anything multiplied by identity will give you the same thing. That's why it's a neutral. It's not doing anything. Okay?
Yeah.
Okay, cool. So this is really handy because if we think about this kind of multiplication, then we could think about something else, which is the inverse of a matrix. So let's say that we are talking about numbers, okay? If you would like to take like the inverse of 3, it will be 1 over 3. This is like doing the opposite thing of what 3 is doing, right? Scaling wise, right?
Yeah.
If you are multiplying with 3, then the opposite thing is to divide by 3, right?
Uh,
Then what is how to represent this with a matrix? We cannot really just divide every number or just take 1 over A and 1 over B and 1 over D and so on. Okay? So what we can do, we can think about what is happening, okay? Like so by writing this equation like that. Okay? We need this inverse matrix, okay? This inverse matrix to be multiplied with our original matrix to give the neutral matrix the identity matrix, right?
yeah.
Because when we multiply both of them, they will give you 1. So this is parallel to this, but for a matrix, okay? So that's how to try to come up with an inverse. And we need to also think about this visually. So what is happening with a matrix? With a matrix, we said that we are changing the area, right? We're changing the
Uh,
area. So if this was our original area, this would change perhaps to this area. The inverse of the matrix is the opposite transformation. So it's as if you are taking this big area and then you are going to this smaller area. Okay. So it's the
yeah.
exact opposite of the transformation. Okay. So
Yeah.
in this slide, I just wanted to show a little animation of the determinant, which is what is happening to the area. If the area was originally A, okay, and then the determinant would be A. If it's A in the original part and then it goes to 2, meaning that it doubled, then this would be our determinant, okay? Okay, so how about the inverse? Again, if this is the original transformation, just magnifying this, scaling this square like so, if this is A, then A minus 1 is doing the opposite of this transformation, okay? Such that if we had our square here, if you take this transformation and then you take the opposite, you end up with the same square, okay?
Yeah.
Okay. So, any questions so far?
No.
Okay, good. Okay, so I think we're making a good progress, so we can jump to the next topic. So in the next one, we will be talking about sine and cosine, okay, and
Okay.
how to think about waves. How to think about waves, because I think this is really not just relevant for machine learning, honestly, it's really relevant to a lot of things, thinking about calculus and thinking about trigonometry as well. Okay, so we have always seen that we take like a sine and cosine and we try to memorize what is sine and what is cosine, right? But let's try to pause for a second and really try to think about the physical meaning of sine and cosine because that's really relevant to trigonometry, geometry, or calculus as well. Okay. So what cosine and sine are really representing is something quite unique. So people have tried to see the relationships inside of a triangle, okay, like so, and they have taken different lengths of these triangle shapes, if we have another triangle and so on. So they can really study the relationship between this length and this other length. But the thing is, what would happen if we try to establish a relationship between the angle and the length? Okay, that's when they came up with the trigonometry and sine and cosine. So let's say, for instance, what will happen if you have a building like so, and you are standing away from that building and you know that have to they have to destroy this building, okay? And you can only measure this angle from you to the top of the building, okay? But you don't know the height of that building and you really need to calculate that building, okay? Just to stay in the safe zone, okay? So this is an example. What will happen if you would like to shoot something on top of that building? You really need to come up with a way to think about the relationship that would govern the change of the angles with different lengths as well, okay?
Yeah.
So that's when people noticed something quite fascinating actually, that if you have an angle theta, if you have an angle theta like so in this triangle, okay, and you take the ratio between this part, okay, and let's call this adjacent. This is the adjacent, okay, and you divide it by this length. If you take the adjacent divided by this length, let's call it the hypotenuse, okay, then you will end up with a ratio, okay. And the fascinating thing is, if you extend this triangle like that, okay, and then you
Yeah.
calculate the same ratios, but for the bigger triangle, so the adjacent divided by the hypotenuse, you would still end up with the same ratio, even for a bigger triangle, like so, okay?
Mm.
So now they notice that there is a function in theta. There is a function in theta, okay? There is
Yeah.
a ratio, and this ratio is governed by this theta, okay, that controls this quantity right here, this ratio right here, okay? So there is a function of theta that is causing this. And if we change this theta, the whole triangle would change, and then this ratio would change, okay? So the thing is, they tried to come up with a name, and they said, okay, let's name this cosine of theta, okay? So now we know that cosine of theta is representing this nice ratio, okay?
Yeah.
And they named the ratio between the opposite and the hypotenuse sine of theta, okay? So sine of theta would be the opposite, okay, divided by the hypotenuse. Okay, so that's nice. That's nice because you can now see the relationship and see why we need really to do this, why we need to come up with something like this. Okay.
Yeah.
Okay, so let's take the same example and try to simplify this representation a little bit to see how this would actually not just come up with cosine and sine as numbers, it will also be the essence of cosine and sine waves. So let's say that we are talking about one length, okay? We are talking about a unit vector. A unit vector is a vector with length 1, okay? So let's say that the
Yeah.
part that we are drawing here is just a unit vector. So this vector is of unit length, like so, okay? And then let's think about the projection on the x-axis. This is our x-axis, okay? So what would be the projection on that axis? If we have an angle theta, if we have an angle theta, when you that adjacent divided by the hypotenuse will give us cosine of theta, right?
Yes.
So what is the length of the adjacent? Okay, this is adjacent, okay? So right now, if we have this vector, if we have this vector lying here on the x-axis, we know that this length will be 1, right?
Yeah.
But as this vector rotates, the projection on the x-axis will be different, right?
Yeah.
But we know one thing. We know that our ratio cosine of theta is adjacent divided by the hypotenuse. Okay, so we know that to get cosine of theta, we take the adjacent and we divide it by the hypotenuse, right? So what is the value of the hypotenuse of our vector? It's 1, right?
Yeah.
So this would mean that our cosine of theta is the adjacent itself. Okay,
Mm.
so this would mean that the value of the adjacent is always cosine of theta. Okay, now we know that the adjacent is always on the x-axis, right? The adjacent is always on the x-axis. Then we could actually say that this x-axis is in fact the cosine of theta. Okay, similar to this, we could think about sine of theta because we know that sine of theta is opposite divided by the hypotenuse, right? So we
Mm.
could just say that this opposite right here, okay, divided by 1 will give us opposite. Okay, so the value of that opposite will give us sine of theta. So what is the value? What is the length of this? The length of this matches the length of the projection on the y-axis, right?
Yeah.
So this would mean that on our y-axis we have sine of theta, correct?
Yeah.
This is truly fascinating. Why? Because imagine now that we would like to construct a wave, okay? Would like to construct a wave. A wave is nothing but a rotating vector inside of a unit circle. How? Because this is now rotating, okay? So let's have a unit circle like so. A unit circle means that it has a radius of 1. So basically, it's just on top of this vector, it's just coming at the end of that vector of our rotating vector like so. Okay, so a wave, a sine wave, you know the shape of the sine wave, right?
Yeah.
A sine wave is looking like that, right?
Yeah.
Right now, we would think about this intuitively and instead of just like trying to memorize why this is a sine wave. Okay. And
Mm.
all of this is coming actually from this rotating vector, nothing more. Because let's imagine, let's imagine our vector right now making a phase value of 0. Okay. The phase value again is the value that you are making, the angle value that you are making with the x-axis. So a phase value of 0 means that this is perfectly on the x-axis. Okay.
Yeah.
So right now, let's think about the projection on the x-axis. Right now, we know that this would be a cosine, right? So
Mm.
the projection on the x-axis will be cosine. So what would be the projection on the x-axis? The value. It would be 1, right? Because that's the length of the vector. True?
Yeah.
Okay. So a signal, a wave, is just coming from looking at this vector at different time points. Okay. So at the first time point, we know the cosine will give us 1. Okay. So let's plot this 1. Okay. Now let's rotate our vector. Let's put our vector here. What would be the projection on the x-axis? It would be a little bit smaller than 1, right?
Yeah.
So let's plot this. Okay. So right now, what I'm trying to plot here is the time progression of our wave. And it's nothing but just varying this vector and just looking at the projection of that vector on different axes. Okay.
Mm.
So right now, that's the projection on the x-axis. It's a little bit smaller than 1. And then it will be here again, a little bit smaller, right?
Yeah.
And so on. And here, and then it will come up until this point that it would be projected to be 0, right? And that's when it will be 0 here. and then it will just keep rotating. And by the way, this is the direction of rotation, okay?
Mm.
So it will be here. So what will be the projection? It will be negative, right? So
Yeah.
it will enter the negative part up until the point it's here, which is the truth of the wave, the lowest point of the wave, okay? And
Yeah.
then it will be here, projected there, and then so it will come up negative, but then it's trying to increase again here and there, trying to go to zero. So it's coming again to zero, okay? And then here and there, it's increasing in value, right? Up until the point it goes to the same place. So it will increase in value up until the point it goes to the same place as the beginning, okay? And this is exactly the cosine wave, okay?
Yeah.
The sine wave is the same, but just looking at the projection on the y-axis, as we just concluded right now. So we take the same vector, the very same vector, and just see the projection on the y-axis. What would be the projection on the y-axis? It would be zero, right? That's why the
Mm.
sine wave is starting from zero. And then when we rotate, then the value is increasing. The value is increasing, right? Up until the point you reach at the peak of the signal, and that's when it's happening here, okay? The projection here is maximum, okay? And so on. You can trace this all the way until you come again here, but always trace the projection on the y-axis, okay? And then you will have a sine wave, okay?
Mm.
All right. Do you have any questions?
Um, no. Alright.
Okay. Okay, good. So let's go to another thing, which is a similarity measure. So as I said in the last part, if we take a vector, let's say a row vector like this, multiply it by a column vector like this, we end up with a scalar, and this scalar would be representing the similarity, okay? The similarity of these two vectors. As we said, if we ignore the scaling for now, or without doing any sort of normalization, okay? So geometrically, we can also represent this. So if we have a vector A and we have another vector B and we have an angle between them, theta, we can see this quantity of similarity in a geometrical way. So we can say that A dot product B will give us the length of A multiplied by the length of B multiplied by the cosine of the angle between them. Okay, so we can do this with linear algebra in this sense. We can do it geometrically in this sense as well. Okay, and both of these will give us the same result. It wouldn't really make any difference. Okay, so whether you take the length of that vector and the length of that vector, cosine the angle between them, and end up with a value, this would represent the similarity. Or if you take the actual values of the vectors, like the end values, okay, because that's x and y for this one, and that's x and y for the other one, okay, and you multiply them, you still end up with the dot product, okay. So if you have the length of the vector and the angle between them, you can do the similarity this way. If you have the actual values of the axes, you can do the similarity or the dot product in this way, okay.
Yeah.
Okay, good. So let's look at something else, which is the feature space and the subspace and the span again. So let's try to discriminate between three things. As we talked about before, if we have a vector like so, and we have a span, okay, we can talk about the subspace of that vector or like a portion or a segment of that space. So what do we mean by the feature space? The feature space would mean that almost all the space that we're looking at, okay? So we can just say that all of this space right here is a feature space. Okay, so any point here is a point nested in this feature space. Okay.
Mm.
Okay. So a feature space actually is a common term in machine learning that we will be using a lot. So we would be referring to any point that might have a sample from our data, and all of these samples, of course, governed by the value of the feature. Okay. So when we say that something is linear, what do we mean by saying that it's linear? Okay.
It means it's straight.
It's straight, right? It's like
Yeah.
a line,
Yeah.
correct? Okay, let's try to represent this word mathematically, okay? And that's really the way I like to think about it, okay? Something linear would mean that we are involving two operations. We are involving summation and we are involving multiplication as well, okay? And this is quite intuitive, because if you look at the equation of the line, you would see that it looks like that, right? So you have multiplication with the slope, and you have addition, which is with the y-intercept, right?
Yeah.
So we can think of something linear. When I say something is linear, you can think of it as taking the value of the x-axis and not squaring the value or doing any kind of thing with the power, okay? Just multiplying this with a value, okay? A weight. Let's say that this is any value, a weight, okay? And adding another weight to this value, okay? And this is linear, okay? Why am I saying this in this way or describing linear in this way? Because you would see linear regression, okay? You would see linear classification. You would also see linear operations in general. When someone tells you that this is linear, this would mean that we are doing multiplication and addition, okay? And we are not changing x value. X would remain x, okay?
Yeah.
Okay, cool. So let's assume that we have a matrix like that. And let's say that we have this column vector A, and we have another column vector B, okay? And we have C as well. So right now, when we say that we can have a linear operation between A and B to get C. So if we can represent C like that, if we can say, okay, let's take A and let's take every element of B and multiply it by 2, and then we will get C. This is something important in machine learning as well and linear algebra, because this would mean that C is not adding any new information, right? Because it's coming from a combination of these two, okay?
Yeah.
It could be good, it could be adding something, okay? But the thing is, it is not independent, okay? So we can say that C is now dependent, okay? That C is dependent on the values of A and B, okay? And there is a linear combination, again, multiplication and addition, okay, to get C, okay? So we can define something from this matrix here. We can define something called the rank of the matrix. The rank of the matrix is the number of rows or columns, okay, the maximum number of them, of the columns or rows that are independent, okay? So if all of our columns and rows are independent, such that you cannot take any columns to get the third one, like what we're doing here, we would say that our matrix is full rank. Okay?
Yeah.
If we have a matrix and this whole matrix is M, and this M is 3 by 3, we say that this matrix is full rank and its rank is 3, okay? Which is
Okay.
the maximum number that we have, okay? This is important because if we have columns like those that are dependent, this would result in making this matrix not full rank. That's the beginning. Okay, so it wouldn't be full rank. And if we are trying to take the inverse of this matrix, we will notice something weird. Okay, so we would say that this matrix would not have an inverse. We wouldn't be able to take the inverse of this matrix actually. Okay, and this is coming from something that is visual and intuitive as well. Okay, if you look at this, if you look at this area right here, what is happening here, what I'm trying to visualize here, is compressing this area into 0. What is the meaning of this? Can you think of something? What is the meaning of changing the area to be 0?
Changing the area to 0 changes the direction.
No. So we just talked about the determinant, right?
Yeah.
So the determinant visually is expressing the change in the area, right? So
Yeah.
if I'm taking this area and then going to 0, this would mean the determinant is 0, right?
Mm.
Okay. So the issue with this kind of matrix right here, that it has a determinant of 0. It goes to 0. Okay.
Okay.
We call this matrix a singular matrix. Okay.
Okay.
This is actually a very nice term because this is like a parallel to something in astrophysics, actually. When we think about black holes, we say that nothing could escape a black hole, right? Not even
Mm.
light. Nothing can escape from a black hole. So a singularity in physics like so, it's like compressing everything inside of this singularity in very tiny space like so, and you cannot go back. You cannot escape from this singularity. Okay? The singular matrix has a determinant of 0. So it got squished inside of this very tiny area. It's nothing. Okay, singularity. Okay, so it's a singular matrix that has a determinant of 0. And the thing is, you cannot escape this singularity. You cannot go out of this singularity. What is the
Mm.
meaning that you cannot go out of this singularity? So you cannot really inverse this transformation. Okay, so if this was A, then you cannot get A minus 1. Okay, and that is exactly why there is no inverse to such matrix.
Okay.
Okay,
Yeah.
okay, so is this clear?
Mm. Can you please explain the full rank is just the maximum um matrix?
So the full rank is the maximum number that we would have from either the columns or rows that are independent. Okay, independent means that we cannot say that A plus B or any value multiplied by B or A would give us C. So there is no linear combination that can be done on A and B to give us the third one.
Okay.
Similarly, A cannot be the result of any linear combination coming from B and C. Okay, so there is no single column that can be calculated from a linear combination on the other columns. Okay,
Okay.
okay, so how about we take a break for like 10 minutes and come back?
Okay.
Okay. Okay. See you later. Hi, Muhammad. Can you hear me? Hello? Hello?
Yeah, hello.
Can you hear me, Muhammad?
Yeah, can you hear?
Yeah. Okay. So let's continue our journey with linear algebra. We will talk about the last thing, okay? And then we will start talking about linear regression, okay? Which will be
Mm,
our first machine learning model, our first machine learning automated way of trying to make a decision. And we would see also the difference between regression and the classification as well. Okay. So I would just need to introduce something that is called left inverse, which is also relevant in solving some problems in machine learning. Okay. So let's say that we have an equation like this. Okay. And we really would like to solve this problem. Okay. And I would tell you why we are trying to solve this problem. Okay. So this is similar to the equation of the line. Okay. This is similar to the equation of the line. So let's ignore the bias for now, or try to imagine that it's a weight, okay, with the
mm,
with the slope, okay. So let's ignore the bias for now. Let's assume the y-intercept is 0, so we are restarting from the origin, okay. So let's just consider this part right here, which is wx, okay. So we have some weight, okay, and this weight gets multiplied by the value of the feature to get the value of the output, okay, the value of the outcome. And as we said, because this is a line, okay, so if this value is positive, okay, it's different from when this value is negative, right? And when we are exactly on the line, this would give 0, correct? So to
mm,
do this kind of discrimination between classes, between categories, we need to see the sign of our output. Is it positive or is it negative? Okay, because this would mean it's belonging, our data is belonging to dog or it's belonging to cat. Okay, so the
mm,
main thing here is that we had our samples, we had a lot of samples. Okay, but why are we building a classifier? We're building a classifier to see that all of these are dogs, all of these are cats. But the real important thing about a classifier that it can draw this separating line, because it is not only important for this data. We say that this data is the training data. Okay, our machine learning model is already exposed to this kind of data. It already sees this data. Okay, but what is really interesting is how our model is going to deal with unseen sample. Okay, if this unseen sample right here, okay, gets drawn here, okay, would our machine learning model be able, okay, to say, okay, this falls above the line, then it should be dog, okay, then it's a classifier, because then it can take an unseen sample that we don't know which category it belongs to, and then it can make a decision on its own and say, yes, it belongs to cat or belongs to dog. Okay. So that's
mm,
our ultimate objective. Okay. Going back, going back to the equation, we need to solve this. Why? Because what is the issue here? What is the real unknown here? Is it X? No, because that's the value of the feature. That's at the X-axis, right?
mm,
That's at X-axis. Okay. So if we know the value of the weight, if we know the value of the weight, then we would know the output. Okay? So what we need to do right now, we need to come up with a way to get the value of W. But the issue is that X is a matrix. X is having a lot of features, right? It's a matrix. So we basically need to get the inverse of X. So if it's an equation, a simple equation, we need to put X on the other side, like so, right?
Yeah.
So we need to come up with a way to solve this. So people have come up with a nice way, which is called left inverse, okay? And it can work with a matrix when this matrix is long matrix, meaning that it's looking like that. It's a long matrix, okay? So it has more rows than columns, basically, okay? So what we can do, we can multiply this equation. Let's say that we have x, and let's think how to get rid of this x here. What is the thing that we can multiply x with in order to just eliminate the effect of this x? So let's think about this together, okay? First of all, x is a long matrix, so it's looking like that, right?
Yeah.
So what will happen if I multiply this x by another entity? Okay, so let's say that we have this and we can multiply it by the transpose of x. And because we have done this, we can invert these values to eliminate them. Okay, to eliminate them. So let's just say that and agree that we cannot take the inverse of something that is not a square. So if I'm gonna take the inverse of something, it should be square, okay? So what I'm trying to do right now, I'm trying to put an inverse, okay, that will eliminate this x, and this inverse should still be square, okay? So I'm putting here x transpose x. So let's trace this. Let's think about this. First of all, we had x, right? We had this part, correct?
Yeah.
I put this part to eliminate x. Let's think about it, okay? So we have here x transpose, and we inverted both of them here. So we have x transpose minus 1 and x minus 1, okay, which is the inverse of this, okay? So just by looking at this, this part will eliminate all of this and will just keep the weight, correct?
Yeah.
Okay, so first of all, this is really good. Okay, so let's see if this is valid because that's X transpose. X transpose is a long matrix. So X transpose will look like this multiplied by X, multiplied by X. Okay, so the result will contain this dimension, okay, and this dimension, which is the same dimension. Okay, so let's say if we have here features and we have samples like that. Then here we will have samples and that dimension will be features, right?
Yeah.
And then the result would be features by features, correct?
Yeah.
Features by features, which is a square matrix, right?
Yeah.
And because this is a square matrix, you will be able to take the inverse. Okay, so this is valid. This is really cool because then we can eliminate x and we can do this. Okay, we can take the inverse of this square matrix, so that's valid now. Okay, now you have done this to this equation. You have done this to this side. You have to do the same thing for the other side, right? So let's think about the other side. We have y, then we need to multiply everything we multiplied here. So we multiplied by all of this, right?
Yeah.
We multiplied by all of this. Then you should multiply with the same thing here. X transpose X minus 1. Okay, multiply all of this with Y, and then you would get W. Okay, because all of this will be eliminated. Okay, so right now we need to solve this issue. We need to solve this equation right here. Okay, in order to get the value of our weights. Is this clear?
Yeah.
Okay, perfect. Okay, um I would leave you with another thing which is called right inverse. Okay, it's built upon the same concept. Okay, so uh you would have your matrix. Okay, but you would have just the inverse looking something like this. Okay, and I would like you to trace this to see if this is correct or not. Okay, and this is happening when X is a wide matrix. So X is a wide matrix like so. Okay.
Mm.
So think about it and see how this is coming from. Okay. It's the same concept basically, but just to trace the dimensionality and see that this is correct, and this would really eliminate X from this side and put it in this side. Okay. Okay. Any questions?
Um. So the left inverse. When do we use this? The left and right inverse.
So we use the left inverse when we need to come up with the value for W. Okay, when you have unknown slope or unknown weight, okay, and you need to calculate this with an equation, okay, and we actually say that this is an analytical solution to this problem because you're using a specific equation to solve this issue. Okay,
Okay.
so it's when you have this form of a linear equation like that, and you need to get the values of the weights. You know the values of X, but you don't know the values of the weights. Okay?
Okay.
Okay, so this will come later. Don't worry about it because this would come later in linear regression, and we would see why we really need this, or why this is a solution. We actually could solve this in an optimized way, different from that. Okay? But this
Yeah.
is a good solution to this problem because it's governed by an equation, okay, rather than an optimization problem or an approximation. But in the meantime, it has its own limitation because it relies on the inverse. Okay. For some reason, you might have a lot of features. When you have a lot of features, the dimensionality of this square matrix will be really huge. And this would make taking this inverse, this procedure of taking the inverse would be very difficult, would require a huge memory, and it would be only an approximation. It wouldn't be a good estimation of the inverse. Okay. So this method has its own limitation as well. Okay.
Okay.
Okay, so let's go to linear regression. Let's think about linear regression and the meaning of linear regression and why we want it in our analysis and supervised learning. Okay, if you remember, we talked about classification. We have some scattered points, and we need to draw a separating line to separate these points, and then we have unseen sample for which we need to make a decision and know its correct category. Okay. Regression is different. Regression is about taking the value of two, let's say taking the value of one feature, okay, and trying to predict the value of the other feature. So let's have an example. Let's say that we have hours and we have marks, okay, and we noticed that there is a positive relationship between the two, such that when you spend more hours studying, you get higher mark. Okay. So you have samples, M samples in this data, and you have a value for hours and a corresponding value for mark. Okay, so right now we can actually draw these two values together. So we can say that we have hours on the x-axis and we have marks. Okay, and we have some scattered points like so, points like that. Okay, okay. So what linear regression is trying to say is that for your data, you know that when you spend 1 hour studying, okay, when you spend 1 hour studying, you only get 2 out of 10 in the quiz, okay? And when you spend, let's say, 6 hours of studying, okay, you get a very high grade,
Yeah.
okay? So we can notice this sort of linear relationship or sort of a correlation between them, okay? Okay, there is a correlation between them. So anyway, what linear regression is trying to say is that instead of having these scattered points right here, we could summarize the relationship between these two by a line. Okay, this line fits in the direction of these scattered points. Okay, so why are we doing this? Why are we doing this? We are doing this because we know our observed data. Okay, but what would happen if you have new unseen sample? You are trying to basically ask yourself what grade I would take if I only study for 5 hours. But then you look at your data and search for the value for 5, but you don't see the value for 5. Okay,
Mm.
so you need this sort of summary that captures this relationship so that when you have unseen data like so, you can just project this on the line, okay, and say, okay, yeah, I will get 5. Okay, so you need to summarize this relationship between these two so that giving a variable, you can predict the value of the other variable. So basically, giving hours, you can predict marks, predict your mark. Okay,
Okay.
and this is general for other things as well, of course, other problems. So we can say giving feature, predict another feature, or given a variable, independent variable, predict another independent variable. Okay. And we can notice something which is nice, that these values are continuous, right? We don't have
Mm.
something binary or something like specific. Okay. These are continuous. So with linear regression, it's nice to predict one continuous, using one continuous variable to predict another continuous variable. Okay.
Okay.
So any problems with the general concept of this?
No.
Okay, good. So let's think about something. Can you see this line?
Yeah.
Which one is better in summarizing the scattered points? The white line or the orange line?
The white one.
The white one, right? Because it's really fitting near the points, right?
Yeah.
Okay, so right now let's try to really put a quantity and measure how well, okay, how good this line is, okay, and how good this one is. So let's define something by which we can quantify this. So let's define something that we can call cost or an error, okay? So how would we measure such cost? How would we measure this error? We can simply measure the distance from the line. Like so, take every point and measure the distance to the line, meaning that for your observed points, the points that are scattered originally, okay, and your line, the fitting line, just measure this distance, measure that distance, okay? That's the distance between what is real and what is predicted. Why? Because our value, 7 hours here, really get the value of 5, okay? But what was the prediction? The prediction is what is the line is predicting, okay? The line predicted something else. The line predicted 7, right? Okay. So that difference between 5 and 7 is now representing our error, correct? Because this point doesn't lie exactly on the line, right?
Yeah.
There is a shift between them that is representing our error. Okay, so we can measure the distance between all of these and then see that error for that point, for the other point, and so on. And then we take the average, we take the mean of that error. Okay, we just average that error for all points, and this would represent our cost. Okay, that would represent our overall error. Okay,
Yeah.
any questions?
No.
Okay, good. So Um, let's think about a formal way, a formal mathematical way of defining this error. Okay, and let's try to think about this together. So we have m samples. Okay, let's say from a coding perspective that we have an iterator I that will iterate on all of these samples. Okay, so right now we need to think about how to put this in an equation. So we would have a value that is predicted. Okay, I will put something here, which is the predicted value. Okay, so let's name the predicted value, and instead of naming this y, we will name it y hat or y tilde. Okay, so this y hat, let's name it y hat. Okay, so this y hat is now belonging to a specific sample, right? So this sample is identified by the iterator I. Okay, and then we take the difference. We take the difference because that's the error, right? We take the difference from that predicted and the true sample, yi, okay? The difference between the two, okay? So the question is, when we are measuring something like the error, would we have something negative, like negative error? No, we wouldn't
Yeah.
have negative error. So we really don't care about the direction of the point. We really don't care if this point is below the line or above the line, right? We just care about the exact value, the absolute value of this error. How far off this point from the line, right?
Yeah.
So that's why we need to make this not just negative, we need to take the absolute value or square this value, right? So
Yeah.
let's square this value, okay? And this will come handy when we talk about something in linear regression and gradient descent as well. So now we have an iterator that will sum these quantities from I, because it's iterator I, and it loops over all the samples. That's why it's terminating at M, okay? And what will happen if we have many, many samples? If we are adding the error, the error will just inflate because we have a lot of samples, right? And we are
Yeah.
adding the error. So we need to normalize this. So instead of taking the error, we take the average of the error. So we just divide this by the number of samples. Okay, so that now we are independent of the length of the data. If the data is huge, this doesn't matter because we just take the average of the error. Okay,
Yeah.
okay, and then I'm gonna put one number here, 2. Okay, and this is put here for something that we call mathematical convenience. Okay, mathematical convenience means that we will use this value later on when we do a specific operation, as we will see. Okay, so it's just a constant that wouldn't make any difference on our variables. Okay,
Yeah.
okay, so that's predicted, and this is the true the true label, okay? And then we can identify this as our cost. So we can say that this is our cost. We'll use this variable j, okay? And this is a function in w, okay? So what is w? W is our slope, okay? Because if the slope of the line, it changes, the line would change, right? And the cost like related to that line will also change, right?
Yeah.
The change of the slope will change the cost. That's why it's function in that slope. Okay, so this would be
Yeah.
our cost. Okay, so this has a formal definition, which is in this equation, and this is called the squared error or the sum squared error, cost function. Okay,
Mm.
okay. So let's go to another part, and I think now we know what we are trying to say, like about um, the linear regression as well. So we know our objective, okay, but we still don't know how to automate this. So we know how to get the cost of every line. If we have multiple lines, we know that this one is not as good as this one. This one is good, right? So right now we need to automate this procedure. So let's think about how to do this. So we agreed that we have a slope for every line, right? So let's just think about a relationship which is very important. Let's say before talking about the relationship, that we have a curve like this, okay? And we have a tangent like that, okay, to this curve. What would be the slope of this line? Would it be positive or negative? To really think about this, let's just try to zoom in a little bit and let's assume that this is our line and this is the part of the curve, okay? So I'm just zooming in inside of this part, okay? So to be able to see the slope of our line, we just take a very small part of y, a very small part of x, and the slope is defined as delta y divided by delta x, right?
Yeah.
We take the difference of y, we divide it by the difference in x, right? So just by looking at this, we see that this point in y is higher than this point in y, right? So the
Yeah.
value on the y-axis here is higher than the value on the y-axis here. So this would make delta y positive, okay? So what about delta x? Delta x of our point here is higher than x at this point. So this also will be positive. So our slope will be positive, right?
Mm.
And what would be the slope if we continue the curve like so and we end up here to be horizontal like this? Delta y, the change on the y-axis, okay, between the 2 points. Let's draw them with another color. So the change on y is 0, right? There is no change on the y-axis, right?
Yeah.
But there is a change on the x-axis. So now the change on y-axis will be 0. On x-axis, let's say 1, or a positive change. So this would give us a slope of 0, correct?
Yeah. Okay.
So that's really important because now we can just look at the tangent and try to think about the slope, the value of the slope. So for instance, this one, you know that the value of y2 is here, y1 is here. So if we have a triangle right like that, delta y, meaning that y2 minus y1, This is y2 and this is y1. Okay. Oh, sorry, this is y2 and this is y1. Okay. So y2 minus y1 will be negative in this case. And delta x, x2 minus x1. So x2 here, x1 here, x2 minus x1 will be positive, let's say 1, if we are stepping with 1, then the slope of this line is negative, right?
Yeah.
Okay, that's really good because then we can just say that we can look at the line and try to come up with the slope. That the slope here is positive, here is 0, here is negative, here it's positive but not as positive or high as this one. Okay, so let's try to think about something else, which is how to relate the minimization of the cost to this curve right here. Okay, so let's think about a relationship which is important in the linear regression problem. We have two variables. We have w, as we said in the last slide, we have g of w, and we have written the cost function. Okay, so we have w, which is our variable. This variable is changing, so it's a variable. Okay, okay, and when the value of w changes, the value of j of w would also change, right? So we need to see the relationship between w and j, okay? So if we drew the relationship between w and j, it could follow something like this, a curve like this, okay? So let's think about what we are trying to do with linear regression. We are trying to minimize this cost, correct? We're trying to minimize this cost. True, because we are trying to get the line that is very close to our points, so it has minimum cost. Okay, so we are
Yeah.
trying to minimize the cost, and we know that our variable is w, so we need to get the value of w that would minimize the cost. So if we are going to this plot and we are plotting this relationship, we need to explore this space. We need to explore the space of w and try to find the value of w that will give us the minimum cost, which is this value. So we're trying to find the value of this w that will give us the minimum cost, right?
Yeah.
Okay, so now try to think about how to use the slope here. Let's think about it for a second. When we are trying to get the slope of something, the slope of this curve at a specific point like so, this is exactly like taking the derivative. Okay, if we took the derivative, okay, of that equation, then we are getting the slope. Okay,
Yeah.
okay, perfect. So right now, let's think about this. So now we know that the slope and derivative are the same thing. Okay, and for this curve, we know that this relationship is governed by the cost. Okay,
Yeah.
so let's think about how to minimize this in an automated way. Okay, so if we have a value for the cost function, if we have an equation, as we said before, we would be able to get the derivative. We can get the derivative of this cost. Okay, so the derivative would be the slope, right? So what is really unique about the value, about this value? Okay, it's looking like this value, right?
Yeah.
So this value is corresponding to the slope happening to be what? Happening to be 0, correct?
Yeah.
So right now we can think about trying to get this value by basically taking the derivative, taking the derivative of the cost with respect to the variable is changing according to, which is w, right?
Yeah.
And trying to make this derivative, because we know that the derivative is the slope, right? And try to make this derivative, this slope, 0, correct?
Yeah.
So if we are able to go to this part here and see that our derivative is 0, this would mean that we know that right now we have the optimal w, the w that will give me cost of 0. Okay? So what I want you to know about this is that I need to take the derivative of the cost function, okay? Take the derivative of the cost function, and I will try to go in the direction of that derivative or try to minimize the cost giving that derivative. So let's think about this now. So let's put our equation. Let's put our equation, which was the squared error. So we have this equation from the last slide. We have y hat minus y of I. All of this is squared, right? And
Yeah.
as we said, when we are trying to get the slope, we can get the derivative. So what I will do right now, I will get the slope of my data. So let's imagine that we have our data scattered like that, okay? And right now I need the computer to think about how to get the best line. It would say that this is not a good line, this is not a good line, this is not a good line, but this one is really good. How to automatically do this? To do this, we are like all of this is under the umbrella of talking about something that is called gradient descent. Okay, with gradient descent, we are taking, we are literally, we are literally doing what the name is suggesting. We are descending with the value of the gradient. So we are basically taking the gradient, which is the slope, okay, and we are descending with the value of that gradient, okay. So this is just for your information, okay? It's coming
Yeah.
really from the name, gradient descent, okay? Okay, coming again to the problem. We have different lines. How would the machine decide which line to use? Okay, so we start off with gradient descent for doing this optimization with a random, yes, random W with a random weight. That's the main that's the main concern, the main issue with such algorithms. We don't know. We don't know where to start from. So we start randomly. Okay. So we start randomly. So let's imagine that we started here. We started at this value, okay, which is a random value for W. Okay. And then we start calculating the cost by just taking the line, okay? It's a random W. So let's say the line was here. It's a random line, okay? We start getting the cost. We start getting the cost, and it will be a huge cost, okay? And then we take the derivative. We take the derivative of this cost function. So let's take the derivative of this cost function, okay? So y hat is coming from the equation of the line, right? Because we have said that we're going to use W, okay, and we're ignoring the bias for now. So it will be W multiplied by X, okay? And Y? Y is the true label. Y is the true label, okay? So right now, let's take the derivative of this quantity. This would be the derivative of the whole bracket, okay? So 2 will be just put here. So it will be Y hat minus Y, all of this bracket and the 2 is here, okay? And this is y over m. That's why we were putting this here for the mathematical convenience, because when 2 gets to this side, it will just eliminate this 2, okay? But again, we're still not done because we need to multiply by the derivative of what is inside of this bracket, right? So what is the derivative of the quantity inside of this bracket? What is the derivative of this? So we are taking the derivative with respect to w. So what would be the derivative of this?
The derivative?
Yeah. So we are differentiating with respect to w, okay? So it's like, let's say if we have 2x, right? If you are taking the derivative with respect to x, it will be 2,
Yeah.
right? Here I'm taking the derivative with respect to w because w is the variable, x is not a variable because x is just any value on the x-axis. So w is my variable. So this will give us x.
Yeah.
Okay. So now this will be multiplied by x. Okay. Okay. And we have our summation here. Okay. So right now we can say that actually for a specific point, we wouldn't even have the summation if we were talking about a specific point. So anyway, we would say that for this, we can plug in another variable, which I will be talking about soon. It's called eta, which is the learning rate. Eta, learning rate. It would really help us fine tune the steps that we are taking to get to the minimum. Okay. Okay, so right now we know the value of our derivative. Okay. And according to gradient descent, we are descending with the value of the gradient, meaning that, as we said, we started here, right? Then we calculated the gradient. It's a high gradient because this is a high slope. Okay, so it does make sense to take a huge step because you are still very far off from the slope zero. Okay, so that's why we're talking steps with the gradient because that's still far away from the minimum. So let's jump here with a bigger step, okay, for W. So now we are updating the value of W. We started here. We would update the value of W. So W new would equal W old, this W, minus this derivative, okay?
Okay.
And then what? And then look at the new position and take another step with the value of the gradient. So what is the gradient again? It's the slope. So this line. So you see the slope of this line is not as high as the slope of the original line, right?
Yeah.
So our step will be smaller, okay? So we'll take a smaller step and then you see the slope getting close to zero, okay? So a smaller step, and so on. So as you get close to zero, your steps tend to be smaller because they are functions of the gradient that you are working with until you reach zero. Is this clear?
Yeah. Yeah. Yeah.
Okay, perfect. So right now, the way that we are going to automate this for the machine to be able to get to this minimum, remember we need to get to this minimum because that's the value of the minimum cost. So we need to get the value of W that will minimize this cost, which would correspond to the best fit, right? That would have the minimum cost. So to make the machine smart such that it can go all the way from this line that was random to this line that is not really random and it's really fitting in the direction of our data, we would need to use something like gradient descent. We need to start randomly, and we need to update ourselves with the value of the gradient each time until we reach a gradient of 0. Okay? It's a gradient descent again because we are descending with the gradient. We are taking the difference. Okay, let's think about what will happen if we started from the opposite side. Let's say we started with a random W and for some reason it landed on this side because it's random, we don't know, right? So we look at the slope again. We look at the slope. This slope is high negative, right? It's a huge negative number, correct? So for this slope, it's high negative. So what will happen? The slope means the derivative. So this derivative is negative. So this value would be negative, correct? So this would mean to get W new, you get W old plus, because that's a negative, and that's negative will be plus, okay? So that W new will land here, such that we are adding instead of taking the difference because the value is negative, okay? So this makes a gradient descent good in both ways. Either you start from here, then you are taking negative, going close to zero, okay? If you are starting from here, you are adding to this value, so you are again going to 0, okay? So you start from anywhere and just take the difference, it will work the same and it will go to 0, okay? Okay, so any questions on this part?
No, no questions.
Okay, perfect. It's really important to try to think about this part, and if you have any questions, feel free to ask. I mean, during this lecture or the upcoming lecture, that's
Okay.
totally fine, because linear regression and specifically gradient descent is like the core concept, not just for linear regression, it's the core concept for the perceptron algorithm, for logistic regression, and later on, even the perceptron and logistic regression are nothing but nodes. Those nodes can be put inside, so we can represent actually any of those. We can represent any of those as just one node like that. And then we can aggregate many nodes and construct a neural network. And if we have more than one layer of those nodes, we say that this is a deep network. Okay.
Yeah.
Okay. So let me go to Matlab and I will try to explain how to perform this kind of uh, coding of linear regression. So let's try to code linear regression together actually. Okay. So can you see the screen well? So can you see the code?
Yeah.
Okay, good. So I will try to just here visualize the cost relationship with the W. Okay. So we need right now to think about what would happen if we have not only J, but if we have well, not only W, but if we have the value of B as well. Okay. So
Yeah.
when we had the value for only W, we were talking about a curve, correct? So we're just like having a curve like this. And this was the relationship between W and J, the
Okay.
cost. So what would happen if we really would like to have this as the equation of the line? So we'd have two variables, W and B, right? So right now we wouldn't be able to represent this in a 2D space. We need a 3D space because we have W, we have B, and we have cost, right? And
Yeah.
the change of W and B would result in a change in the value of the cost. So let's try to visualize this kind of relationship. Okay, so this relationship would look something like that. We would have W, would have the value for W, okay, and then we would have a value of B and the value of the
Yeah.
cost, okay, and then we would be talking about a grid that is like drawing a surface like that, okay, such that you can really investigate this and see how it's changing, okay. Now, what would be our goal? What would be our goal? Giving this shape that looks like that, okay? What would be our goal? We have W, we have B, and we have cost. What was our
To
goal?
minimize.
To minimize the cost, right? So in this curve, if we started at value, at this value, this is a bad value, right?
Yeah.
Because looking at this, this is a high cost, and we need to minimize this cost. So we really need to go to this point, right?
Yeah.
We need to go to this point. We need to see the corresponding value of the weight, a corresponding value for the bias that will give us this point. And now looking at this 3D shape, we can say, okay, if I started here, I can take a step with the gradient in that direction, and then the gradient would get smaller, 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 as long as we get close to this minima, right?
Yeah.
Okay, some important terms here. If we get stuck at this point, we say that this, yes, is a minima, but this is not the global minima. We say that this is a local minima, okay? And we get to this point and say that this is our global minima, because this point is really good. This is our true minimum, right? This is the minimum that we want. So this is the global minimum. And the issue is that we could stuck at the local minimum, okay? If we don't iterate enough, we could stuck at the local minimum. And if the slope here gets very close to zero, we could get stuck at the local minimum. That's why we don't only have gradient descent, we have different kind of optimizers. We have something like RMS probe, we have something like momentum, we have something like adaptive momentum. So gradient descent is not the only thing. There are some variations on gradient descent to be able to handle some issues that might happen with gradient descent. Okay.
Yeah.
Okay, good. So our shape again will be something like that, such that if we could imagine that we are projecting this from above, could you see the projection of this from above? It will look like that. Okay. I am
Yeah.
showing you this because right now you can imagine that a 3D, a 3D shape like this can be
Yeah.
decoded from something 2D. How? Here is the same thing, okay? It's at the same figure, okay? We can see that our shape right here is having a maximum at the yellow part, right? It's having a
Yeah.
maximum at the yellow part and having a minimum at the blue part, correct?
Yeah.
So right now we can not have a 3D shape, we can instead have a simpler 2D graph like this that is color coded. Okay, because right now we know that this color is corresponding to the maximum and the blue color is corresponding to the minimum. So we can basically, instead of having the 3D shape, we can represent this relationship between W and B using circles. So we can say something like that. We can have something like that. We can just draw some circles and say that the bigger circles, okay, are the high values, okay, so these are yellow, okay, and these are the blue one. So as we get closer, we're getting close to the minimum, okay? So you can imagine that this is going inside of the screen. This is going to the minimum, okay? And here we can put W and we can put B, okay? So we can put W and B, and here with the circles, we are including the cost. So that when we start here with W and B, we are trying with gradient descent to go to the minimum cost, okay? So right now we have encoded the 3D shape inside of this 2D shape. Is this clear?
Yes.
Okay, perfect. So let's think about linear regression and how to try to get our variables W and B for the best fit, the best line. Okay, let's try to really think about this. Okay, so let's try to write this together actually. Okay, so that would be linear regression. What we want to do right now is to come up with some points, some scattered points, okay? And we need to get the line that would fit inside of these points, okay? So in Matlab, we can define something like this. So we can define some points that go from 1 to 10, something like that. So that would be our x, and we can define y to be also like that. And then we can have a figure, okay? And then I'm going to plot the values of x against the values of y, and then I can do something like that. Okay, I'm gonna run this. So here I'm just, x will be a row vector, okay, from 1 to 10, okay?
Okay.
You can see this, it's from 1 to 10, okay, stepping by 1. And y will be also from 1 to 10, okay? So I'm just plotting some points together that are linear. So 1, 1, 2, 2, 3, 3, 4, 4, okay? So that's our x-axis from 1 to 10 and y-axis from 1 to 10. Is this okay?
Yeah.
Okay, perfect. So each value is basically scattered with its corresponding value, okay? So we have these points, we have these scattered points, and we need to get the line that would fit in the direction of those points. Good?
Yeah.
Okay, so let's try to think about this. How will we start optimizing this issue? So we need a line, right? And we know that the line is governed by this equation. So we can substitute m with w, right?
Yeah.
So we have two things that we need to get. We have w that we call weight, and we have b that it's called y-intercept. But for the problem of linear regression or classification in general, we can say that this is called the bias. Okay, so we need to get two things. We need the weight and we need the bias. Okay. Okay, as we said, we would start from a random number, from a random value. Okay, so we can initialize w to be random. Okay, as you can see, I'm just running this part here. You would see that the value is changing, okay, every time I run this. So it's really random. It's really random, okay? And I would initialize w in a similar way. So it would also be a random value, okay? Now let's have the concept, the logic of linear regression to help us how to get to the minimum and really get the best fit for our data, okay? So let's think about the part of gradient descent, okay? How to start optimizing this. So we can look at the part that we were just explaining, okay? And we would see the derivative of the cost function very clearly. So let me just try to rewrite this so that we can look at both of them at the same time. So we have our derivative, right? We have our cost. So let's start from the cost actually. Let's make it easier. So we have our cost J of W and B, right?
Yeah.
And we define this cost like so. I equals from 1 to m, and then we took y hat minus y squared, right? And this is a phi. Okay. So we have this cost function, and we said that to get to the minimum of that cost function, we are gonna look at the slope. We're gonna look at the gradient. So we started by taking the derivative because we are going to update ourselves with the value of the derivative. So we'll take this cost function. We will take the derivative of that cost function with respect to w. And we took that derivative and it was 1 over m, right? Y hat minus y multiplied by x, correct? Now we have another variable. Now we have another variable that we need to optimize for, which is b, correct? So we need to take the derivative of this cost function with respect to b, okay? We know that this y hat is coming from the equation of the line. It's wx plus b, right?
Yeah.
And this is just the value of y, which is an actual number, okay? So now let's take the derivative with respect to b, okay? So it will be y hat minus y, which is the whole bracket, okay? This 2 will eliminate this 2, okay? So it's still 1 over m multiplied by the derivative of what is inside. So what would be the derivative of what is inside with respect to b? This is a number, so it wouldn't have a derivative. Its derivative would be 0, right? What about
Yeah.
this one? The derivative of this one with respect to b?
W.
With respect to v, w and x will be like a constant, okay? Because the only variable, because we're differentiating with respect to b, so that's the only variable, okay? So this will give us 1, okay? Because that's our variable that we're, differentiating to. And all of this is constant, so all of this will be 0, and this is like getting the derivative of x with respect to x, which will give us 1. Okay, so now we're getting the derivative with respect to b, and we're getting the derivative of b, so this will be 1. So this will be multiplied by 1, so it wouldn't be multiplied by anything, okay?
Yeah.
So now we have these two very important equations that we can use. So right now we know that we have value for w, okay? We need to update the w value. We would take the old value of w minus the derivative with respect to w, right? And we have this equation that we will use to update the value for the bias. So bias, the new value, will take, sorry, that's the bias, okay? So we'll take the value of the bias, the old value, minus this quantity, right?
Yeah.
So let's code this right now. Let's code this because that's our equation that we are going to use to update this weight, okay? So let's take the difference between y hat and y, multiply this by x, and then take the average because that's summation and then dividing by the numbers. So that's the average, right?
Yeah.
And that would be the derivative Okay. Okay, perfect. So we need y hat minus y. So what would be y hat? Y hat would be the predicted value, right? So we basically take w, which is the random value in the beginning. We multiply it by x, right? And then
Mm.
we sum b. Okay. So right now, this would give us the value of y hat. Okay, that's the predicted value giving the random initialization of w and the random initialization of b, right?
Mm.
So how about we look at this line? This should be a random line, right? So
Yeah.
let's try to visualize this line and see how bad it was performing in fitting this data, okay? And see also how it would change if we run this multiple times, okay?
Mm.
Okay, so let's have some points for x, and then we would have our y hat, and we plot this value, okay? So let's have some values for x. So let's have x values, okay, some x values. So let's have some x values that will go from -10 to 10, okay? I will just use those x values just to substitute in the equation, okay? And then get y hat value, okay? So this would be y vals, the corresponding values of y will be w, x, plus b, okay? And now let's try to plot this. So in Matlab, there is a nice way of plotting on the same plot. It's called hold on. So I'm holding on to the first figure, and
Mm.
I will try to plot the values that we have for x and y. Okay, so how about
Mm.
we run this and see what happens? So let's see. So we have y vals. So we have x vals here. This will give us those values. Okay, but there is an issue with them because that x vals got minus got 21 values, and this one got only 10. This was happening because we used the x, we didn't use x vals, so we should have used x vals. Okay. Okay, so you see this?
Mm.
That's the line that it got randomly, okay? So let's run this again and see if this line would change, okay? See, the line is changing.
Yeah.
Every time I run this, the line is changing. So this is really saying that this was a random initialization, okay?
Mm.
Now, what we are trying to do, we will try to get this line and try to move until we go to the best fit, okay? And how we would do this by using, of course, the derivative and then try to minimize the cost. Okay. Okay. So right now we can calculate y hat by just taking the x values multiplied by the weights and then sum the bias. Okay. Now let's update our, so this value right here is y hat. We can update our weights. So our weight value will equal weight, which is the old weight, right? Here I'm just trying to put the equation. Here I'm not doing anything new, okay? So W new will equal W old minus the derivative, okay? So that derivative is the mean of the predicted minus the true multiplied by X. So I will put this here. So this would be the mean of y hat minus y. Y hat minus y, okay? And this is multiplied by what? This multiplied by X, okay? And there is an error in this line, I would like you to try to think why this would give an error.
Mm-hmm. Mm-hmm.
So first of all, there is a problem, okay, that we are taking the mean, okay, of y hat minus y before multiplying with x. But we should be taking the mean after multiplying with x. If you look at the equation, we're taking the mean of the values after multiplying with x, right?
Yeah.
Okay, so summation and dividing by m, that's the mean. So that's fine. So let's think about y hat and y. Y hat and y. There is a problem with this, which is that y hat and y are row vectors. If you look at y, it's a row vector, right?
Mm.
Y hat is also a row vector, okay? So y hat minus y will give a row vector. So let's run this. This will give a row vector, right?
Yeah.
But x is also a row vector. So if I'm trying to multiply them like so, this will give an error, okay? Because you cannot multiply a row vector with a row vector like that, okay? If y hat minus y is a row vector like that, we need to transpose x so that it's column vector, okay? So that we can get the dot product, okay?
Okay.
Okay, so this should give us scalar. Okay, good. So let's see if this works right now. When we transpose x just like that, yes, and it gave us one value, which is a scalar, okay?
Mm.
Okay, now if we took the mean, we will be making a mistake. Why? Because when we multiplied y hat minus y, we multiplied this with x, we are multiplying and then adding the values together, right?
Yeah.
So we have already multiplied and added the values together. So back to the equation, we added the values together. So we just need to normalize by the length, okay? So I just need to divide this by the length. I need to take all of this divided by the length of x. Okay, good. So this would be our new value for w. So let's see what would happen for the value of b. b will equal the value of the bias, okay, minus this quantity. So it would be the same, okay, but without x. We're not multiplying by x, okay?
Mm.
And then here we will be getting the mean. We will be getting the mean because in this one, there is the summation here, okay? And we're dividing by m, so we'll be taking the mean. And we will be literally taking the mean, not just the dividing as we were doing here by the length, because here we are not doing dot product with anything. So we are not summing before normalizing. So we'll be taking the mean. So let's look at this. Here we would need to get rid of this. Okay, now we are not multiplying with that, and we'll be taking the mean. Is this fine? Okay, so now we need to do this in many iterations, and that's the whole trick, because we are updating with the gradient. As we said, we are updating with the gradient. We need to do this for many iterations, in order to be able to go to cost of 0. Okay, so let's try to do this. So we will put all of this inside the for loop, let's say for I equals 1 until we go to like a very huge number. Okay, and then we end this. Okay, and then let's think about the cost that we have. Our cost function can be written directly. So we have a cost value, at every step, that would equal y hat minus y. This would equal the mean, and this would be multiplied by half actually. Okay, y hat minus y, and then we square this. Okay, but why are we doing this? This is the cost function itself. This is the main cost function. Okay, this is the main cost function, because the cost function, the original cost function got half, that's the half, and then 1 over m summation, that's the mean, so that's the mean, y hat minus y, okay, and then we square this, so that's the cost value, okay? Okay, now that we have the cost, we have a way to update our W. We need to terminate from this loop. When would we terminate from this loop? We would terminate when the cost achieves 0, okay? So we would put an if condition. If cost equals 0, then we would break of this, break outside of this loop, okay? Okay, it's very difficult to have a cost of exactly 0. So sometimes we put a very small value like tolerance or something like this, a tolerance value that is very small, and say if the cost is lower than this tolerance value, let's define this 10 to the power of minus 6 or something. It's a very small value. So if our cost is smaller than this, we assume that we should terminate, okay? But for the time being, I will just put it as 0, okay? And then after this loop, we should get the value of W and B that would have the minimum cost because we are going in the direction of the gradient. So what we need to do after doing that, we need to plot another line that should be able to get our fit. Okay, so let's repeat this. Let's repeat this. Now the value of W and B after the loop should be updated. Okay, so if we do this again of X values and we hold on and plot, this should give us our good fit. Okay, and we could comment this because that's the initialization, which was random. Okay, so
Yeah.
we can look at this and see what would happen. Okay, or perhaps we can make this like these are a lot of iterations. It will take forever. Okay, we can um, use different values and just see what will happen. Okay, so we should plot this from minus 10 to 10. So let me check that we are plotting this correctly. Yep, so there should be something that we didn't look at. So I think we didn't include, yeah, we didn't include the variable of the learning rate. I forget about it. So the variable of the learning rate will be like changing
Okay.
our steps, because our steps were really big when we are jumping with the gradient, such that we are going in different directions. That's why it was exploding and giving very high values. Okay, with the learning rate, the value eta that I didn't include in the code, yeah, I forget about it in the code. It's a very small value. It's called the learning rate, and it's able to like change the way we are jumping, the scaling. Okay, and just take a ratio of it. So we can put it with a very small value, like this value. Okay, and then we can put this eta in our equation as well. Okay, so we can take just a subset of this with respect to eta. Okay, can you see it now?
Yeah.
That's our line. It's a perfect fit for our data. Okay. And if you look at the code, if you look at the values, you would see that the value for W is 1, which really makes perfect sense because the values that are increasing together 1, 1, 2, 2, 3, 3 are actually having a line of a slope of 1. Okay. And W is the slope. It's slope of 1. And B should be small. It should be close to 0. And you can see it's a very small value. It's a 3 to the power of minus 14. It's a very small value. Okay. And our cost value is getting smaller, smaller, smaller with more iterations, which is really good. Okay. And our last value is actually 0. Okay. Is this clear?
Yeah.
Okay. I would like to show you a nice animation because I have already written this code like 2 or 3 times during the other lecture. So I would like to show you this animation. I still didn't like show the other group this animation, but I think it would be nice to have a look at this. So check this animation of the line. Can you see this?
Yeah.
The line is going into the direction of the best fit. And this is precisely what is happening. Here I was visualizing with every iteration what is happening. Okay. So you can see how the line is going towards the best fit.
Yeah.
Okay. In the meantime, can you see this figure on the left? This is in fact a 3D figure. Okay. You can see the value of B, the value of W, and the value of the cost. Okay. And you can see how we started from here, a high value for the cost, and then we are going down, down, down. We are minimizing the cost, you see? We're going down in the value of the cost like so. Okay.
Yeah.
So we are going below, we are going down, close to 0, close to this value of 0. Okay. And the nice thing is you can see the value for B, right? You can see the value for B. Can you see
Yeah.
this part that is still iterating?
Yeah.
Is still trying to achieve what? Is still trying to achieve almost 0 for B. And this is exactly what we are trying to do. We're trying to achieve 0, right? For the value of the bias of the y-intercept. And the value of W should be achieving 1, right? If you look at the value of W, you would see 1, and you would see that our iterator is trying to achieve this value of 1 for W. Okay?
Yeah.
And that's how this is done for linear regression. So, as a general concept, I would say if you are doing linear regression, if you are doing classification, if you are doing anything like that, and you need a machine to optimize your code or you optimize your loop, then think about a cost function. Okay. Think about your error. What's the thing that is causing an error? Then take the derivative of that cost function. Take the derivative of that error. Okay. And then go in the direction with something like gradient descent. Go in the direction of the gradient and try to get the value for your weights that would minimize that cost. Okay. So again, come up with an error or cost function. Take the derivative of that cost function to minimize that cost function. Okay. This is really important for regression, for classification, for deep learning, for anything like that. Okay.
Yeah.
Okay. So that was it. Okay. Good luck and let's keep in touch. And until I see you next time. Okay, thank you.